All right, so add this title down. The chain rule. Okay, so before we start, I just want to summarize what we've been doing. And so you don't have to write this part down, but first thing we did was we just started looking at random functions, and they could be linked by pluses or minus, but when they look like that, they are often just the power rule takes care of them. Then after that, we went to, well, what if we had functions that were being multiplied, and we learned the product rule. And then we learned the quotient rule to take care of quotients, their derivatives. So today, we are doing everyone's least favorite, the composites. Okay, so we're going to learn a rule to help us take derivatives of composites. And just like how we started, let me just give you an example and see if you could figure out what I'm doing to my generalization of f and g. So let me pick an equation, and this isn't a composite yet, but I'm going to start off with just one of them. F of x equals sine x, and g of x equals, say, x cubed. And let me take their derivatives individually before I compose them. Yeah. Oh, it is recording. So the derivative of sine is cosine. And then the derivative of x cubed is 3x squared. So these are by themselves individually, but I'm going to put them together. I'm going to do a composite. So let's call it f of g of x. Hey, so what this means is I take the g of x equation and I plug it into the f of x equation. So here was f of x, and I compose the g of x inside there. So you guys are working with composite functions now. So here's the derivative. I'm going to just give you the derivative, and you can tell me what am I doing to my my f and g equations. So these are them by themselves separately, but when you get a composite, you have to realize its parts. So the derivative ends up being something like this. And that's the derivative. Okay, somebody tell us, what did we do to the f and the g equation to generalize it? So its derivative, what did we do? Or what did I do here? Yes.
You take the derivative of f of x and times the g of x times minus 1 of the derivative of g of x.
Okay, the derivative of f of x, not times, but just still composed. And then times it by what?
Times minus 1 of the derivative of g of x.
Good. Like that? Minus 1?
Because it was actually derivative of g of x is 3x squared, and then the
Oh, this is still a 3. Sorry. Yeah, okay. My 3 looks like a 2, right? I'll fix that. All right, so this is what we have. So this is the f prime, and this is the leave the g of x alone, and then this is the g prime. here then. Okay, so when you go to take a derivative of a composite, this is what you guys need to do. You need to realize the outer and inner function. So you realize, oh, sine is the outer function. You take its derivative, it becomes cosine. The inner function stays the same. So like one derivative at a time. Then you link it with a multiplication, and you then take the derivative of the inner function, and you leave it on the outside. So product rule linked by plus, quotient rule, you guys had the low-d high minus, so linked by a minus, and then the composite is linked by a multiplication. You're just multiplying your inner pieces. Okay, so let's try one more, and just so that we start to get better feel for these. And let me give you 3 pieces, and easy ones to identify, inner, outer. Okay, so first thing is you got to realize there are 3 layers in this, right? There is the outer layer, cosine. There is the second layer, tangent. And then finally, there is the inner layer, x squared. It's like a little onion. First layer, take its derivative. Derivative of cosine, leave the inner pieces alone. Okay, that was cosine's derivative. You got the first layer. You toss it in the decompose. And then you do the middle layer, which is tangent. So you gotta say times the derivative of tangent is secant square. Leave the inner piece alone. You still have your x squared. That's the second layer. And then finally, the last layer ends up being that. So you have to keep on doing that layer, which is 2x. And that's your derivative. Okay, let's see. Usually when you do this, your final answer, we try to put these pieces to the front when we're dealing with trig, so we don't mistaken to multiply them by these inner pieces of the trigonometry argument. So that one goes out here. And then the rest could probably, I could probably pull that minus sign out, but the rest just gets tossed along. Yeah, I think that's all I really need to do for something like this. This is inside the argument of the sine, so we can't really do too much with that. We can't break it up into sine and cosine and start canceling. Yeah, so that's all we could do with something like that. Okay, we got to try a couple more so you guys start to get the feel for your pieces here. Okay, so say we have a new one. And it looks like that. All right, so this one, you could treat it like 3 layers or you can treat it like 2 layers. There's an outer layer, which is the square root right now. And then there's a square layer. And then finally, you have your inner layer, which is this one here. But you can also rewrite this. Oh, it's not a derivative yet. Just a rewrite like this. And that will just be 2 layers now. Okay, so when you rewrite it like this, there's an outer layer, which is the power rule. It's that one. It's 3/2 power. And then your inner layer is this one. So So when you go to take its derivative, you're going to take the derivative of the outer layer. You're going to bring down the 3/2. You're going to do 3/2 minus 1, which is 1/2. Okay, that's the outer layer. Its derivative done. And you are not supposed to do anything with the stuff in here yet. Leave it alone. Then you can say multiplied, and then you can multiply by the derivative of this inner layer and put it there, which is 2x. Okay, let's see how much simplification we need to do with this. This part has a positive exponent, so I don't need to bring it down, and I probably just want to write it as a big quotient. So I also could see that this 2 and that 2 divides out, and maybe that x and that 3 just gets put together. So there was actually nothing that I really need to put in the denominator. I can just leave it like that, or if I wanted, leave my answer like this. So both of these are good answers. The back of the book will probably convert them back to square roots like this one. Okay, so just 2 layers here. If you rewrite it like that for this one. Okay, let's try a couple other ones. Let's start to combine the chain rule with the product rule with the quotient rule. Yeah. This one? Oh, it's supposed to be 2/3. That's correct. Because the 3 goes below the 2. Okay, some fix up here. So it's actually 2/3, and it's 2/3 minus 1, which actually is negative 1/3. So now we're going to get some fractions here. This part's not going to cancel anymore, right? Okay, did you guys bring your whiteout tape? I love whiteout tape. Look, I didn't make any mistake now. Okay, now when we go to simplified, that has to be brought down and tossed into the numerator in order to make that power positive. The 3 now doesn't really cancel anything. This 2 times that 2 is a 4, and that x stays up there. So we'll get this simplification instead. Yes, the rules of radicals here, that's supposed to go underneath that 2, like that. Okay, so good fix. Let's try some combinations of these chain with a product. And if you're ready, I'll give you a big problem to do. A combination of all of them together. All right, so say we have an x squared and we are multiplying by a 1 minus x squared. So first thing is we need to identify the overall bigger operation here. What's the bigger operation? A product rule. It's this product times this product. But when you do the derivative of the second piece, that's where there's a outer inner layer. So you're going to approach it with the product rule in mind. Derivative of the first piece, leave the second piece alone. Leave the first piece alone. You took its derivative already, so you just leave it alone. And here's the derivative of the second piece. The second piece is a is a chain rule because you have a 1/2 power. So you would do 1/2 and then subtract 1, so negative 1/2. Leave the inner piece alone, and then times it by the derivative of the inner piece, negative 2x. So derivative of the first piece, leave the second piece alone. Leave the first piece alone, derivative of the second piece. But in that derivative, there is a chain rule that appears. So let's practice simplifying. Let's see, this 2 and that 1/2 goes away. This whole thing needs to be tossed into the denominator. This x can now be multiplied with that x, and then the minus could be put there. Did I get all its parts? I moved this one down, the half and the 2 cancels, the x and the x makes x3. And I still have this side. Okay, we need to get one big denominator, so we might want to even change this into a fractional power so we can start working with that fractional power. So instead of saying square root, I think I'm going to go in and change that into a fractional power because I have another fractional power there. And all we're doing here now is we need common denominator. We need this denominator. So this side, we need to times it by that denominator, top and bottom. Okay, so when you multiply these, this one times that one, they're like bases. They're 1 minus x squared bases. So it's a power half and a power half. Your rules of exponent says add them. So it's 1/2 plus 1/2, which is ends up just, well, 1 plus 1 is 2. So 2 over 2 is 1. So these two multiplied together results in just this. This one times that one. And then the 2x is still there. No distributive property. They're all just multiplication. So now you got common denominators. And you can just write it over that denominator. And let's multiply through. 2x minus 2x cubed minus x cubed. So I distribute the 2x, distribute, and then that's just minus x3. Then I see x3 and x3 here, so I get 3x3. Okay, and I'm going to leave my answer there. So you got to get a feel for knowing that this is in its most simplified form. Sometimes maybe our books might do this. But that's good enough for me. You can write it like this if you are trying to match up with the textbook. Okay, so the math gets fairly confusing with square roots. Let's do this with a quotient rule. And also practice with a square root for the quotient rule. Okay, so first thing is to realize it's a quotient rule, but the d low is a composite function. So a chain rule must be done when you do the composite of the d low. So when you go to work this one derivative, low, d high, derivative of x is 1, minus high d low, and here's the chain rule. So I might want to treat it like a 1/3 first. So then the d low is the derivative of this low piece, and it's a 1/3. Leave the inner piece alone. Subtract 1 from this 1/3, so you're going to get negative 2/3. And then the derivative of the inner piece, which is 2x. So that's the low d high minus high d low, a chain rule, over the square what's below. So the below is that, but when you square it, it will be 2/3. Okay, let's work on simplifying here. Okay, we need to slowly work with the numerator piece. So in the numerator, it looks like I have a x squared plus 4, but I'm going to write it as a 1/3 power instead of a cube. Over here, I need to toss this entire thing in the denominator. The 3 lands in the denominator, the 2 is in the numerator, and then the x and that x makes a x squared. Okay, that's just this part, cleaning this whole thing together. Then I now realize that this whole thing needs a common denominator. And that's the denominator. That's the common denominator. Yeah. This one? This one?
Yeah.
Like that?
No, like, as in, when you read it, when it looks that things like the x squared plus 4 2/3 has that thing.
This one?
Yeah. So when you do those two equations, you know x squared plus 4 is the power 1/3. Why is the denominator 1 of that equation rather than x squared plus 4 is the power 2/3?
Oh, because it's separated by a minus right here. Are you saying this? Why isn't this one's denominator the same?
Yeah.
Right now I haven't. I'm just working with just this piece. All of it together still has this at the bottom.
Oh, okay.
So I'm still not. I need a denominator just to clean up just that part first, and then that denominator is going to still apply to it. Okay, so this one wasn't that. This one came from this one only. Okay. So now I'm just working with the top piece right now. I need that 3x squared plus 4 2/3 denominator. You can start to like incorporate this in, but I just didn't want to do this one just yet. I'll do that one last. Okay, so now just up here, you guys have this one times that one. 2/3 times 1/3 actually creates just a 1. So that means the 3 is there, but then you just have this expression, x squared plus 4. And now they are over that denominator. And then you have a minus 2x squared. And then you still have that denominator at the bottom that's here. Okay, so far so good? Yeah. You mean here? Here? Oh, this is just the low part, unchanged. Oh, that's the rule. That's the rule about your conversion from a radical to a fractional power. And if I'm working with other fractional powers, I probably want to change that radical to that so I can start to combine it with the other pieces. If you don't like the radicals, then you have to change these other ones. Well, if you like radicals, you have to change these other ones to radicals also, so you can start working on it together. Okay, now that you get to here, this part down here will land right there in the next line, because the next part to that is saying you have this times the reciprocal of that. So your next line, now you have a 3x squared plus 4. That's just all of this. And then this part lands right next to it. So that's your next line. And then they are the same base, an x squared plus 4 base. But one is 2/3 and one is, oh, another one's 2/3. So then that means together it is 4/3. Oh, and then there was this, oh, yeah, so it's 3x squared plus 4 to the 4/3 now. And in the top, you could start to distribute through. And then collect like terms. To the 4/3. And that will be your final answer. Okay. How do you guys like the math there? So with these square roots and quotient rule, cleaning it up is tricky. Now, if it was a free response question, you guys could sort of leave it maybe up to like one of these points. But if it's a multiple choice, most of the time they have already cleaned it up to here. So now you have to practice simplifying and seeing how you would get it to be all nice and neat like that one down there. Okay, so let's do a couple more of these. And I want to do some trig one. I want to do two comparison of a trig piece so you guys can start to see the difference. Okay, so these look really similar, but the inner and outer functions are different. So when you see it written like this, it actually means this. And when you see it written like this, it actually means this. So when you do your homework, make sure you can tell the difference, because if you go to take a derivative, this one, the sign is the outer layer, x squared is the inner layer. This one, the square is the outer layer, and the x squared is the inner layer. So with trigonometry, we write it like that, but we mean like that. And they don't always put parentheses when it looks like that, but you will know that that's actually n sign. Okay, so you can see that their answer is different, their derivatives is different. The derivative, you would start with sine's derivative, which is cosine, and then you leave the inner piece alone, and then you times it by 2x. This one over here, when you go to take a derivative, you actually do the derivative of the power 2 first. So you're bringing 2 down, you reduce the power, it's a 1, you don't have to write it, but I wrote it there. And then you do the derivative of sine, which is cosine x. So result into two separate ones. But oftentimes I see students just mixing them up. They see that, but they think that means this. So they do this route, but it means something else. And then sometimes they see this, but they think it's inside with the X. So um, uh, you have to make sure you put them in the right spots. Okay, how are you guys feeling about the chain rule? Okay, so with these, you have to practice because this is the last of the shortcuts, and we can combine it with all rules now. So let's do a big problem. That was not the big problem, guys. Times. Should we times it by something too? Let's times it by secant. Or no. Maybe we'll just times it by tangent. X. Alright, here's our big problem. Okay, you guys try this one.